Okay, so in the last video, we talked about what you would do in order to update the value of W. And that requires an essential thing, which is the slope of the tangent line at this point right here, which is this is wherever your guess is, and this is the slope of the cost function at that point. And so that's a really crucial part that we need to revisit again. And it's actually called the derivative. So this is essentially the derivative of J with respect to W. And this is often represented as dj dw. This is not a fraction, but it's kind of like a fraction actually, but it's this is essentially just means the derivative of j with respect to w. Okay? And in order to get this, we would have to take the derivative of this function over here with respect to w. Okay? And I'm gonna assume that you know a little bit about the derivatives for this part, but in case you don't, then it's okay to gloss over this part. So we want to take the derivative of, so I'm gonna get rid of that. I'm gonna rewrite our cost function. J is equal to 1 over 2m times the sum I equals 1 to m of y minus y hat squared. I think that's what I wrote before, right? And yeah, so I'll actually get rid of this summation for now, because it actually doesn't do anything if I have a summation. So I'm going to get rid of the summation for now. And so over here, what would happen here if I take the derivative with respect to w? This is wx, by the way. Wx. We would have to use this thing called the chain rule. So since I'm assuming that you're familiar with a little bit of calculus, so you would take this 2 and bring it down. So you would have 2 times, and we have this factor over here already, right? So there's 1 over 2m times 2 times whatever this is, y minus wx, and then multiplied by this, whatever this is, right? And that's the chain rule. And so yeah, so this would basically, the 2 would cancel out over here, and we would get 1 over m times y minus wx times x. And if you think about it, this was sort of the error. And if I do 1 over m, and I have, like, let's say a lot of examples, and I actually included the summation that I crossed out, what would happen is that this essentially takes the mean. If you ignore this, then that's just doing it for one example. So let's say we're only doing this for one example, then this would basically be the error times the input, and this is the input, right? And then this gives us the slope of the cost on actually just only one example. On one example, it's only one example because we're only using one example over here. And yeah, so this is the slope of the cost on one example with respect to the input, which was W. And so this gives us the slope of the cost function on one example with respect to W. And if we had included the summation over here, you can do this on your own, but if you included the summation here and you included the 1 over m here, this would be the mean of the slopes across all the examples. And so let's say according to example 1, so this is W, and I'm going to make J1. J1 is essentially, J1 is y1 minus y1 hat. Our prediction, so the real value for the first example and the prediction for what we're trying to predict for the first example, subtract them and then square it. So this would be J1, right? And let's say that this is something like this, right? And let's say that this is similarly, there's a J2 for the second example, right? Like that, which is also like a parabola. And let's say we're at this value right now, which corresponds to this point on this graph and corresponds to, let's say, this point on this graph. Now, so this is our value of W currently, and it corresponds to two different points on two different graphs. Now over here, the slope is positive, and so this would inform us to decrease the value of W. And here, the slope is actually negative, and we would be increasing the value of W. And so if we took the mean between the updates from both of these, that's essentially what would happen over here. The mean would be closer to 0, I guess. And let's say instead of this, the point that we were actually on that corresponds to this point over here is this one, this one over here. So it's not actually this. Oh, I gotta redraw that graph. So I gotta redraw this graph real quick. So let's say this was our point W on this graph, and then this was our point W on this graph. Now over here, the slope is negative, so we want to increase the value. And the slope is negative here, so we want to increase the value as well. And so if you take the mean of the two of them, then basically they're both telling you that you have to increase the value. So you would be more likely to increase the value of your parameter W. And so that's essentially how the update function works. That's how you would calculate it, calculate the slope of the line at that point from before. And so I just want to make it clear that before we had said W is equal to the original value of W minus because we want to decrease the value when the slope is positive, increase the value when the slope is negative. And you have an alpha, which is your learning rate, times the slope, right? But now instead of using the word slope, we're actually going to just write dj dw. And so this is what we call like the update function. This is the update function for W. So now we're ready actually to put all of this together. So remember, step number 1 was to guess what W is. And this is sort of a random guess. We're going to guess W equals 0, right? And then guess number 2, step number 2 was evaluate. Evaluate the value of W. How good is it? How bad is it? And that was the J cost function. The cost function that we called J before. And step number 3 was to update. And this is the update function, where essentially you want to find the new value of your parameter W by taking the old value, subtracting your learning rate, which could be, let's say, 0.1, and multiplying by the slope. And the slope in this case is calculated based on a derivative, right? You take the derivative of this cost, how bad your model is doing with respect to the parameter, right? And that gives you the direction for the update. And the alpha is used to dampen that effect, I suppose. And then number 4 is to repeat. So I just want to talk about one more thing. And so this actually, one second, this is all collectively called gradient descent. Gradient descent is the name of this algorithm or this chain of things. And so I just want to talk about one more thing, which is our choice for the value of alpha, right? What is alpha, I guess? Alpha let's say this is your graph that tells you, you have W here. For different values of W, what is your cost? Um, and let's say that you're over here. This is your value of W right now. And so this is your cost. All right. And you determine based on the slope of this tangent line that's negative that you want to increase your value of W. Alpha will tell you by how much to scale that factor. So it's essentially the amount that you're changing is your slope times your alpha, right? And alpha is a thing that can be chosen by you. You're free to choose what alpha is as long as it's greater than 0. And it has to be greater than 0 because of the directional thing, right? Up here, if alpha was just negative, then there would be no point in putting the negative sign over here at all. And you would just have plus the slope, and you would update in the wrong direction, basically. And so if you have a small value of alpha, small, let's say 1 times 10 to the power of negative 6, right? Very, very small. Then what you would do is you would be here and you would increase your value of W, but very, very slightly. So maybe you would go to this point here. So you would iterate to that. And then you would iterate again to that. And then if you repeat a lot of times, then eventually you would get to the bottom over here, right? And you're almost guaranteed if you use a small value for alpha that you would be taking an update in the right direction at all times. Now, the problem with that is that, that iterating process of repeating might take a very long time computationally, I suppose. So if it takes too long, then your value of alpha might be too small. Now, on the other hand, if it is big, right? Let's say it's too big. What would happen is that we might update it this much, right? And then the cost is, let's say, this, right? Which is still fine. The cost is still decreasing, but it's going sort of overshooting your ideal value of W, right? Which is not a problem in this case, but it could be a problem if your alpha is just way too big. Now, if you get too greedy, you want to finish the process of gradient descent very, very fast. Then what you might end up doing is you might end up choosing a value of alpha that updates from here all the way to here. And this actually has led to an increase in the cost. And so technically, we were correct about the direction, but the amount by which that we updated was too large. So what we can do instead of choosing a value of alpha that's like, let's say it's too big, it's 1,000, right? It's way too big. Instead of doing something that's too small or too big, choose something that's just right. And that might be 0.1 or it might be 0.01 or, it might be different things for different situations. And we might have to tune the value of alpha. And the process of tuning parameters like the value of alpha. So I want to make it clear that the value of alpha itself is not learned, but it is used to influence the learning process, right? How much you update is influencing the learning process, how fast you're learning, if your learning is numerically stable or not, and all of those things. And the process of tuning parameters like alpha that decide how your training is executed is called hyperparameter tuning. So alpha is a hyperparameter because it's a hyperparameter because it's used to decide the learning process. Things like W1, W2, B, and so on would be considered a parameter because that's what's used in learning, and that's what's being learned, right? But this is what's influencing the learning process as a whole. And you would have to experiment with different values for alpha in order to get to something that would be ideal for your use case. So that would be under the process of hyperparameter tuning. And so now that I've explained a little bit about hyperparameter tuning and the value of alpha, I think that's it for this video.